Good morning, good afternoon, or whatever time zone you're in. Welcome to the third in a series on storage benchmarking performance from SNIA ESF. This time we're focusing on block components, and this presentation will be starring Ken Cantrell from NetApp and Mark Rogov from EMC. I'm David Fair. I'm the chair of the Ethernet Storage Forum in SNIA. I have to start with some of the background stuff. This is a legal notice. There's no tests on this, by the way. I want to make sure everyone understands that at the end of this presentation, this webcast will be posted on the SNIA ESF website. I'll link to the BrightTalk presentation. And the foils will also be posted as PDFs at that point. You are welcome to use those foils. Understand they are copyrighted by SNIA. The only requirement is that you use any foil in its entirety and you don't modify it. And you're going to hear all sorts of things said today. Just want to emphasize there are no warranties, express or implied. Any information you learn out of this, you use at your own risk. But have fun. So here we are. Ken is from, as I mentioned, from NetApp. Mark is from EMC. I assume you guys have watched part 1 and part 2, so I'll say nothing more about that. The only thing I'm going to say before, last things I want to say is I will be monitoring the questions as they come in. Ken and Mark have run through this presentation multiple times. There's a lot of material. We're probably going to save most of the questions for the end, and we certainly won't get to all of them. So the questions that you ask that don't get answered here will be posted to a Q&A blog on the SNIA website afterwards. And the last thing is the charter of SNIA ESF is to provide vendor-neutral information on storage networking over Ethernet. And what we really want from you is feedback, so please give us ratings that we're doing this for you. And with that, let me hand it over to Ken and Mark.
Thanks. We're glad to be here again. The voice you're hearing right now, I'm Ken Cantrell.
And I'm Mark Rogov.
And as he said, we are in the third of a series of presentations on storage performance. So we were initially engaged to give a talk on file performance. And some of you have asked, when are you finally going to get to file performance? We promise it's coming. But as we started to do that, we realized that we really need to give some background before we get to that point.
And before we move on, I would like to acknowledge the International Women's Day today. And make sure that all the women present on the call feel welcome and a part of a bigger family. And with that, let's move on. So in session number 1, Ken, what do we do?
Session number 1. So we began talking about terminology and context. So we wanted to ask the question, if you're going to talk about performance, what are the words that you need to know and the basic ideas that you need to know? And then if you have those words and you have those ideas, and you have 2 different performance charts, how do you decide which one's better? Which system is better if you're comparing 2 of them?
And with that, we went through a couple of scenarios and explained where the context makes metrics matter. And that was really what's mostly important. Whatever the context your business has or your application has, whether that be rack units, AC temperature measurements, IOPS, or anything else. Right.
If you want to know more about that and see the really cool walkthrough we did, you should watch session 1. You should watch session 2, because in session 2 we said, okay, now you know the words and the ideas. Now you understand how to compare 2 systems, but why would 2 systems have different performance? So we painted this picture of a solution under test, so that solution under test goes all the way from your client back to your back-end storage and includes everything in between. And I'll make a quick comment. We've had some feedback during our dry runs on this presentation about the fact that that looks like a really traditional system as opposed to perhaps a scale-out system. And our premise is that this is a fundamental concept that applies no matter how complex or how simple your system is, and it applies no matter what. So we began with that and said that which component matters?
It's a slow one, clearly. And the interesting thing about the slow components of the solution under test is that the slow component is something that we would call a bottleneck. Those bottlenecks always exist. So that slow component or the bottleneck could be kind of moving across your solution under test depending what kind of adjustments are being made. And then we presented 3 performance principles on how to address those bottlenecks. But before we move forward and start talking about block storage and block components, one of the things we wanted to share is a piece of news that Ken found, that IDC posted that enterprise storage vendors combinedly shipped 33 exabytes of data just in one quarter, third quarter of 2015.
So just 3 months, the enterprise storage vendors shipped 33.1 exabytes of storage. And we've seen a number that the world market as a whole was much, much higher, but we couldn't find a number we could quote that you could go look up on that. But
yeah, you just have to pay for that out of the number, and this one felt to be free and available. But one of the things that we wanted to do was to say exabyte sounds very, very strange to us, even though we're in the industry and we've been doing it for a little while, so we decided to put it in perspective. And the perspective is that if we divide 33 exabytes among 7.4 billion of living humans on this planet, everybody is going to get about 4.5 gigabytes. Is that a lot, Ken?
not anymore. Because I can buy a terabyte hard drive, but when I started that was actually the size of the drives when I started.
But the good thing is that to give even more perspective, you can fit 1,541 copies of our first PowerPoint presentation and fill up those 4.5 gigabytes of data that you're entitled because you're a human living on Earth.
That's pretty cool. And we mentioned this in part because we said we need to give some background, right? And part of this background is that we're shipping a lot of storage. In other words, we're shipping a lot of physical media that data can go and reside on. In a previous life, I talked to somebody who really wanted to do file performance. And part of what I told them, because I was making them do block performance, was, look, not everybody does replication. Not everybody makes snapshots. Not everybody does SMB. Not everybody does NFS. Every single person who's doing storage at some point is going to store their data somewhere.
On the block storage somewhere.
On block storage somewhere.
So what about cloud, Ken?
Cloud is just somebody else's disk. It just means it's not close to you. But if we're going to understand overall system under solution under test performance, we have to understand the block performance. And specifically, we really need to understand disk performance, drive performance, flash performance. There's a lot of other components to block storage. There's fiber channel controllers and switches and PCI cables and protocols.
Zoning and all that jazz.
But we wanted to focus today on disk performance, on drive performance, on flash performance, because that's even the core of block performance. And block performance is the core of all storage performance.
Very good. So with that, the agenda for today is that in the beginning, we're going into explaining reading and writing. Just explain why is there a difference between the two and what the fundamental real difference between those two is. And then we're going to go into the technology and have a little bit of fun of explaining how does technology work. And specifically how do flash drives work and how do block spinning drives work. And then we're going to go into explaining what happens if you combine more than one of those together. And once we know understanding that, then we'll go into the performance fun. Show you a little bit how those numbers stack up and what happens.
What happens if you put it all together?
What happens if you put it all together? And Dave, do you have any questions so far, or should we move on?
Go ahead and move on. No questions so far.
Excellent.
Awesome. So let's just jump right into numbers because I like numbers. So all the numbers that we're going to show today come from a subgroup at SNIA called the SNIA S3 Technical Working Group. They've developed a specification for exactly how you should test hard drives, and specifically flash, but hard drives as well, in a very vendor-neutral way. And so they involve
a repeatable way.
In a very repeatable way. That's an excellent point. So I'm going to pull all these numbers from that. You can go look them up, and we'll have a link at the end of this presentation to where you can find more on that methodology.
And by the way, speaking of links at the end of the presentation, we have a couple of slides that are kind of hidden away. Once you go and download the PowerPoints, which PowerPoint is going to be available just like the PDF, at the very end in the appendix, you're going to find the links that we may be referencing here.
Okay. So what we're going to look at here is reads versus writes for a hard drive, for spinning disk, a SAS hard drive, 15K RPM, 146 gig, doing random 4 kibibyte.
Whoa, wait a second, Ken. So you've done a lot of those numbers, but there's one particular word that I think we haven't defined well yet, and that's random. 4 kibibytes, I think we understand, and the audience should be able to understand.
You should know what a kibibyte is if you attended the first one, the first of our webcasts.
That's right. We spent a lot of time explaining their kibibytes versus kilobytes, but random, that's a new word.
Well, then tell us what random is, Mark.
All right, so since Ken likes numbers, I like pictures. And here's a picture in my attempt to explain random to anybody who really wants to know. If we look at the keyboard, and I'm making the general assumption that we all have seen a keyboard in our life at some point, and using that keyboard, we say the keyboard is now a storage device. It's a disk drive. And if it's a disk drive, then every single key is an addressable block within the disk drive. And when we type out a phrase like common, a quick brown fox jumped over a lazy dog, the way we're pressing the keys to type that phrase, from the keyboard's point of view, the keys are not connected and not next to each other. They're all over the place. And when those blocks being addressed from the drive's point of view are all over the place, that's what happens, and that's what we call random. Consequently, if we look at everybody's favorite password, 1, 2, 3, 4, 5, 6, this is an example of a sequential word. Because every single key is positioned right next to the one before it.
So, and this is a relevant example because at least traditionally with spinning media, every piece of information is stored in a location on the drive, and those locations are all numbered, and those numbers the close numbers sit next to each other, and they all proceed sequentially, throughout the rest of the disk.
That's right. And a good example for that would be watching a DVD or a Blu-ray movie. We put a disc in the player starts reading. It's reading all of that information sequentially that's represented on the screen with a pretty picture.
Okay. So now we can talk about random I/O.
So what we have here is random I/O, which means that from the disk's point of view, the information sent to that disk for both reads and writes was all over the place.
It was all over the place. And we'll explain why that's really important in a minute. For the purpose of this chart, I just want you to see that our numbers are in this 100 to 500 range. And depending on who you ask, the right numbers might be a bit higher if you were to test perhaps a newer drive. But the ranges here are the most important. We're going to cap out around 500 IOs per second doing random 4 kibibyte IOs.
And the other thing is that Ken and I have done this for a little while, and the first time we saw these numbers, we said they're a little high on the reads than we remember. And then we realized that a lot of times, a lot of vendors quote an average number between reads and writes.
True.
And here you have two 100% reads and 100% writes compared to each other, and you can see how writes in this particular test have been slower.
But it really doesn't matter because the point is to compare that to Flash. So that little bitty 514 down in the corner and the 133 down in the corner are the numbers we just saw. The orange is a consumer-grade SSD drive.
Wait a second. Consumer-grade, are you trying to tell me that I can go to a store and just buy one of those and stick it in my laptop?
Yes.
And particularly this, I'm going to be able to do 60,000 IOPS at 4K random?
Yes.
Wow.
And what I find just mind-boggling is if we move on to the next one is that there's a lot of different kinds of flash devices out there with some variations in technology. So we're looking now at 2 consumer-grade flash drives. That would be the orange and the purple. And then 2 enterprise flash drives. Those would be the green and the pink or whatever it is over on the right-hand side. But you can see that an enterprise drive is capable of doing 750,000 random 4 kibibyte IOs per second.
That is incredible.
It blows my mind. I mean, what would it take? I mean, you've been doing this for a long time. Are these numbers hard to achieve?
If we're trying to talk about a traditional storage array that we're constructing from either one of the manufacturers and vendors that we know, that's a pretty tall task. I'll be honest. And knowing that the single drive can deliver 750,000 IOPS is blowing my mind.
So I'm going to make an unprofessional comment here because it's just fun. Mark and I do this presentation over and over again. we don't have a set pattern for who talks about what slides, and it would be fun if you all could see us because we grin and ask each other questions that have almost always gone the other way in our dry runs. So this is a lot of fun. But, you know, huge numbers.
And this is one of the reasons why we wanted to show the flash right at the very beginning. And if you still see the itty-bitty 514 in the left corner, that's the normal spinning drive. In fact, it's not just even normal. It's a pretty fast 15K spinning drive. And comparing 514 with 750,000 is ridiculous.
Right. So this leads to a very obvious question. Is disk dead? Is there any reason to do spinning media at all anymore?
Surprisingly, yes. Remember how we said the context makes the metrics matter? This is just a metric. For some businesses, the context could be not about the IOPS or not about the speed of that performance. It could be about capacity and a combination of things, and it could be about sequential versus random type of stuff. For example, I read an article in Forbes how Google is putting forward a request to create new spinning drives because YouTube, as a subdivision of Google, is growing at an astonishing 1 petabyte a day rate. And to store all of that data, they actually saw some benefit to having spinning drives with a couple of additions, like multiple heads and bigger drives and a couple of other things that they put forward.
And, you know, I found a blog for a company that does their entire company purposely and consciously on spinning drives because it's cost effective for them. You know, so they've got over 40,000 spinning drives because that's what they do, and they found a valid business use for it.
But clearly, the cost of drives and flash points is constantly moving. There may be in the future a point, maybe in the near future, perhaps very, very soon, when flash cost is going to drop so much, it will be more cost effective.
But
perhaps. But knowing what a single drive can do is one of those fundamentals we wanted to put forward in front of everyone.
And for the rest of this presentation, our goal is to focus on the performance and the performance characteristics, really, of both hard drives and a flash. So there are other things that come into play, you know, like power or cooling or something, but we're going to focus today just on the performance elements.
And this is a time for David to interrupt us and see if there's any questions we can address before moving forward.
Go ahead at this time.
Okay. So let's go right in. Let's look at the technology. If we look at the drives, normal hard drives here on the right, they have a whole bunch of different parts, and most of them are moving, or so it would seem. And the flash drives have no moving parts. It's a very basic way of looking at things. But let's look a little bit further. Let's look at what happens in a spinning drive when an I/O request comes in. And interesting thing is that regardless whether the I/O request is a read or a write, the drive generally has to seek the right track and then rotate and wait for the right sector to come over so that we can perform the I/O operation. And that's a very important. We seek and then spin.
And that rotation, when we talk about 15K, that's basically how fast it's rotating.
That's how many rotations per second that platter is actually doing.
But that's where the time comes in, right? It takes time to rotate to the right spot, to seek to the right spot, and then to start to read that data or write that data.
That's right. So when something is sequential, for example, you don't need to seek anymore and or even rotate for that matter, because your next sector is positioned right under the head, and you can proceed forward with reads and writes. Even though they still can talk about how reads and writes themselves are different magnetic operations, the seeking and spinning takes more time than anything else.
And that is exactly how flash works as well, right?
Absolutely incorrect. You should know better. You've seen these slides before. So let's look at the flash drives. The flash drives are a completely different world. So the first thing about the flash drive is they're constructed on these little things called negative AND gates, or sometimes called NAND gates. Most of the times actually called NAND gates. And those NAND gates are electronic little tiny devices, sometimes they're called cells. They're put together in groups, and by default, when they're ready to be used, they all come in set with 1. So in order to write anything on them, a process needs to go ahead and change a 1 to a 0, which is kind of interesting. If you have to write all 1s, do you have to do anything on the flash drive?
you have to do nothing, which is amazing to me. My brain says that something that is uninitialized is all zeros. Or you don't know what it is. You have to go and give it some value before it means something. And I think, as you're describing it, uninitialized really means all set to ones.
That's right. But where it gets really interesting is when you need to overwrite that 1, 0 in a group of these NAND gates. That's where all of a sudden you find out that you can't do that unless you erase the entire group together. And by erasing, that means you're writing once across the entire connected groups.
So I can write a 0 to just one spot. If I want to write a 1, effectively, I have to touch a lot more.
You have to touch a lot more and use a lot more power for that matter.
Okay, so I have a question. And if I want to optimize my storage performance, then I could do that by just writing nothing but zeros?
You can make a whole database out of zeros.
If you wanted to be even faster, you could write one entirely of 1s, which you would have to do nothing.
Oh, okay.
Yeah, David shared with us this really, really nice cartoon from Dilbert, where someone claims to have made a database out of zeros and nothing else, which was phenomenal. I love it. But let's take a look at how these cells get organized into actual devices. So we take a NAND gate and a group of them, and we connect them all together, and we call that a page, where one page can carry 2 kilobytes, 4, 8, or 8 kilobytes, or maybe even 16 kilobytes. It kind of depends.
Depends on the vendor and the exact implementation.
And then when you add those pages up together, again, a very normal number of 128, 256, 192, whatever the amount the vendor decided, that constitutes a flash block. And what's interesting about that block is that it is the entire block that gets erased to ones. So think about it this way. The I.O. is going to come in, I'm going to start writing into the pages, literally writing chunks of zeros. And at that point, say, whoops, we need to overwrite it and overwrite that specific page. We'll need to go ahead and erase the entire block.
And that erase cycle is a big problem, right?
It is a big problem. It takes more time, it takes more power, and it erases the entire thing. So you can't just overwrite a single page.
It erases an entire
block. Okay. Which means that what flash devices have, and this is on the right of the image there, we have a little memory map in there that's pointing to where the address of the block with data lives. So instead of overwriting data in the block, we will just redirect that write to a new block that's been cleaned, and now it's going to contain the data, and we're going to mark the block that had old data as dirty.
So this is a fundamentally different process than we had with hard drives. In that hard drives, every block basically, and for those of you who understand this, I'm ignoring bad block remapping. We're just going to pretend that doesn't exist for a moment. But in general, the blocks had a location on the disk. And you always knew, where am I going if I'm going to this address? Here, these blocks of data can exist in all sorts of different places on the flash drive, and it depends on where they had been remapped to. So sometimes, in our picture here, perhaps the upper left-hand corner is 0 through 100. Perhaps other times it's 1500 to 1600. They change their location.
That's right. But what's even more different from these devices than normal drives is the fact that we can't leave those dirty blocks dirty forever. There has to be some sort of a process that goes on and sequentially, one dirty block at a time, cleans them out or erases them.
Turns them back into ones.
Turns them back into ones, makes them clean and available for future redirects.
Because if we didn't, we would eventually run out of things that were all ones that we could turn into zeros and ones. Something has to go back through and give us places to write data effectively.
That's right. And the process that does the cleaning is called garbage collection. And it has a clear performance implications because when you have something on the drive that goes through and erases those dirty blocks and cleans them out into cleans, that's taking the processing power of the drive.
Well, and it seems like it would be the gating function, in that if I don't have any of these blocks clean and I want to write something, then I have to wait for the garbage collection to clean something so that I have something to write to.
Kind of similar to how the spinning drive has to wait until he spins to the spot and then rotates to the sector.
Okay. So basically, the speed of which I can do garbage collection would be the maximum write speed that I could possibly do, because I'm always going to have to be, there's always has to be someplace I can write to, and I can't go faster than my garbage collection could catch up.
That's right.
Hey,
at least in a steady state world where.
Right. Yes. Go ahead, David.
Yeah, interesting question. So NAND is not the only kind of flash. Do these problems go away if you used a different kind of flash like NOR, or does it just flip from ones to zeros? The problem.
That's a very good question, and we will answer that question in the blog. Because
okay,
quite
fair enough.
Yeah.
I don't want to talk about other types of gates, because almost 90% of all flash devices are using NAND gates today. We'll just leave it at that.
Well, and the other thing I would say is, at least in our dry rounds, we had representatives from 3 major vendors who sell all flash systems. None of them had an issue with the basic logic flow that we're talking about. So even if it does work differently in different devices, it's not probably going to in the devices you're going to come across and buy.
That's true. So let's summarize it all together. One of the interesting differences between the spinning drives and flash devices is this acknowledgement sensitivity to different workloads. Because the flash drives have this remapping layer on top, they turn every workload into random workload.
Effectively. I mean, you might get sequential I/O within your block, but you keep picking different blocks. The blocks are in different places, so it's effectively random.
So no matter what I/O you're going to throw at this, it will be always random.
Okay.
Whereas if we look at the disk drives, how do disk drives take random versus sequential?
Well, we kind of talked about it in that sequential is fast, random is slow. And so, I think kind of the secret sauce that vendors have been doing for years and years is trying to turn random I/O into sequential I/O, because we hate random I/O. Random I/O is a terrible thing. So it's a completely different mindset, really, and set of optimizations that you need to throw into play in order to optimize the performance.
So when we say terrible thing, what we really mean is the response time was growing during the random workload.
Or it's much higher.
Or when it was higher than sequential. And flash devices, here we have a completely different concept. Here we have sensitivity not to sequential versus random, but write versus reads.
Right. And so what we've tried to show with the big orange blocks, in part, is what's slow, right? With flash, it's a difference between reads and writes, not between random and sequential, and writes are your problem. And really it's not even writes, it's the garbage collection behind it. And then with spinning media, it's not about reads versus writes as much, it's much more about sequential versus random, and you want sequential I/O. Because random is slower.
So those numbers that we showed at the very beginning when we had flash drive versus spinning drives, can we assume that they're taken when garbage collection is not on?
No, actually, so those were actually worst case numbers with consistent garbage collection. The numbers are actually much, much, much better for fresh out of the box systems before garbage collection kicks in.
So in other
I didn't want to
if
show
I buy a new drive and I stick it in my laptop and I just all of a sudden kick in the write test, I'm expected to see even higher than 750,000 IOs for the enterprise level.
You definitely can.
Using PCIe.
Yeah, there was a bunch of stuff on there. I think that number was probably a PCIe number.
I think it was a PCIe number, which for everybody in the audience, you're unlikely to be able to use a PCIe connectivity to your drive in your own laptop. So don't necessarily expect to hit 750,000 IOPS with a drive, unless you have something special knowledge on how to connect.
Okay. Let's move to the next section.
Well, let's see if David has any questions that need our answers.
Oh, go ahead and move on.
Okay. So we tried to show what kind of performance can you get out of a single drive, at least in general, right? We didn't go into lots of detail, but the big scale. And then why? Why do those numbers look as different as they do? The next question would be, what if you need more than one drive? And why? Why would anybody ever want more than one drive if you can get numbers like that?
Well, the why is very simple, and we have it right here on the screen. There's 3 main reasons for why connecting more than one drive together. The best one and most important one is capacity.
So if you, and again, part of this is if you don't want to change your application, You know, if you want your application to simply have access to a lot more storage than a single drive can provide, it would be really nice if there was some way to combine multiple drives, make it look like one drive, and yet be a lot bigger. And so that would be one reason. Protection would be another reason. Perhaps, you know.
It's kind of important, though, that if you all of a sudden lose one drive out of a collection of 2 drives that you've been enjoying.
Well, or even more basic, right? We were talking about a single drive. You have a single drive, all your data's on it, you lose your single drive, then you're in the place of almost everybody at home with their laptop who doesn't back up and it's all gone, right? So you want some way.
Have you been there, Ken?
I may be there right now. And then we've got performance, right? If, especially in an older world of spinning media, what do you do if you want more than 500 IOPS and you don't want to change your application? We need a way to combine drives together to give you higher performance than you could get out of a single drive.
And since we're here performance experts, we're going to talk about performance in terms of reads and writes consistently.
Right, we will break them out
throughout the entire presentation.
So the way that we have done that traditionally is through something called RAID. Stands for Redundant Array of Inexpensive Disks.
Was it inexpensive or independent?
Yeah, it depends on who you ask. I think the official thing we found said inexpensive, although independent makes a lot more sense when you're looking at Flash.
Especially
at least historically.
Given the vendors and how much 33 exabytes of data being shipped, how much of that data is really inexpensive?
So RAID, you could do RAID at all sorts of different places. You could do RAID at the client if you wanted to. In an enterprise storage context, it tends to be done at the storage controller. This is part of the magic that your vendor brings to you is a good RAID implementation. And what
it's kind of tucked away behind almost the storage controller, so most effectively don't see it.
Right. The idea is that your clients, your host, your applications have no idea that RAID is occurring, and it's an invisible process. So what we're going to do really is kind of take multiple drives, combine them together into a virtual drive or a physical drive, or logical, that's what I'm looking for. Yes. A virtual drive or a logical drive. And so let's look at how we can do that.
So the RAIDs are separated by different RAID levels, and we're going to talk through some of them, but not all of the RAID levels.
Right.
And the first one we're going to touch on is RAID 0, or something known as striping without parity. And here, if you look at the screen, you're going to see the client sending a couple of IOs, a 0.1 and a 1.1, to this logical virtual drive concept that he has. And it's the logical drive which is going to take those IOs and split them in a way where one is going to go to one drive, the other one's going to go to the other drive.
So our virtual logical drive is twice as big as either one of our physical drives. Assuming if they're the same size, it's going to combine the 2 physical drives together into its exposed capacity.
That's right. Or how we said it here, if you look at the icons on the top, we said capacity is 100%, which means that if you take the capacity, the usable capacity of the drives participating in RAID 0 set, and you add them all up together, 100% of that usable capacity is available when you're doing RAID 0. Right.
And I prompted that question the way I did because I wanted the clarity here, because as we go through all of this deck, whether it's for capacity, protection, or performance, the idea is how much of my raw capacity or my raw performance, or really the protection one's a little different, but for those, is visible through my virtual or logical. And with RAID 0, 100% of my initial capacity is available.
And then when we say raw capacity, it is the capacity of the drives individually added together,
right,
as opposed to the capacity that's exposed to the host through the virtual logical disk that we have in here.
I think we're clear. So we get all of our capacity. What do we get for performance or for protection? How much protection?
Nothing.
Right. So if you lose one drive, say in this one you lose your 0.1, having the 1.1 is nice. But it doesn't tell you what the other one was, so it's meaningless. You effectively lose all of your data if you lose one drive.
If you lose just one drive. And now, does RAID 0 really have to be just with 2 drives?
No, you can use as many drives as you want. The more drives you put in, statistically, the more likely you are to lose data.
What about performance, Ken?
So performance. All of the performance capacity of your original drive is available. So, yeah.
So if they do 100% of all reads and all writes are available.
Right.
So in other words, from the host point of view, I'm writing to the single one gate virtual logical gate coming in, and I'm feeling that it's working twice as fast as a single drive would have been, because now I have two drives in there.
Exactly, and that's true for both reads and writes. So this one's easy. I like this one. It's a good place to start.
Okay, well, the next one is RAID 1, which is mirroring.
Still pretty easy.
It's very simple. RAID 1 is the only one RAID that we would like to cover today that always consists of just two drives.
That's true.
Otherwise, mirroring it doesn't quite work. It can be combined with other things, and then it's still mirroring between an object and an object.
Yeah, let's not make it more complex.
Let's not go more complex. So here we have the same idea. The host is sending two IOs, 0, 1, and 1, 1, and the logical drive is mirroring them in the matter that 0, 1, and 1, 1 goes to one drive, and the same 0, 1, and 1, 1 goes to the other drive.
So our two drives are exact copies of one another.
They're exact copies of one another.
It's exactly what I do at home.
Which means that the capacity available is now half of the raw capacity that we have.
Because we effectively just see one drive.
That's right.
Yet the other one's just a copy.
And we're paying that capacity to gain the protection. And the protection in this case is one drive, and it doesn't matter which one of these drives goes down. We have the other drive, which means the data is intact and available.
Okay. So I'm going to switch up our order from the way sometimes we do this and say, let's look at the write performance first. Because with the write performance here, we're looking at half the performance that our physical drives could give us, because every time a write comes in, it has to go to both drives. Both drives have to say, I'm done, and we're waiting on whichever one is slower. So our write performance is half that we could get if we could actually access both drives individually.
So if both of them can do 100 IOPS, for example, for performance, we're not going to be able to do 200 IOPS. We're only going to see 100 IOPS,
right,
even though there's two of them out there.
And I did that one first, because the reads are a little more complex sometimes.
Well, not in this case. The reads here actually is 100% available, because in good implementations of RAID 1, we're going to be able to read data from both drives at the same time.
So we could, for example, read the 0, 1 from one of the drives and the 1, 1 from the other drive.
At the same time, simultaneously, and not have to wait for one read before the second one is processed. So the host is going to be benefiting from the performance abilities of both drives at the same time.
Okay. Are we ready for the next one?
We're ready for the next one. The next one is RAID with Parity. And it applies to RAID 3, RAID 4, RAID 5, and if we talk about multiple parities, RAID 6 and RAID DP and everything else with that. But what we have here, let's take a look at simple single parity right now that we have on the screen. If the host sends their two IOs, 0 and 1 to the logical drive stripes these between a subset of drives and then creates new data called parity, and then sends that data to another drive.
So again, kind of restating this, if we take out the little green P there, 0, 1 and 1, 1, it looks exactly like RAID 0. It's functioning exactly like RAID 0, except when we add in the P, this is brand new information we've created by somehow combining the 0, 1 and the 1, 1 to create data that we can use to recover either the 0, 1 or the 1, 1 if we lose them.
So let's first look at the capacity real quick. The capacity is the N drives, or number of data drives that we have in this set. So
the way people tend to talk about this is that you might say something like, and what this picture would be, this would be a 2 plus 1 RAID 5.
Where N is 2, number of drives, P, number of parity drives is 1.
Right.
So the capacity is the sum of capacity of the drives dedicated for the data.
Yep.
And the capacity that provided us for the drive with parity is not available, and therefore capacity is not available there. Right. What about protection, though, Ken?
Yeah, and I'm going to throw in one just nitpicky thing there, in that you made the comment about a drive dedicated to data. In a lot of these, that parity information moves around from drive to drive, but it's the number of drives that we've said we want to use for data is in.
I completely agree.
Okay. So, for performance,
first was protection.
Oh, for protection. We can lose P. We can lose as many drives as we have parity bits.
Okay, now the performance is kind of more interesting. The read performance is exactly the same as number of data drives. But the write performance can be described using our favorite...
It depends. I love it.
Favorite phrase. It really depends.
If you work with a performance person, you hate that word because that's their answer to everything. Okay, here's what it depends on.
This is a very complicated slide, so just read the words on the bottom and later on come back to the pictures for the reference. And listen to Ken.
Yes. So there are two cases for doing writes. One would be large sequential writes, which I don't have pictured because they're easy. With a large sequential write, all of your data can go into memory, and your storage controller that's implementing RAID could calculate the parity in memory. And so you could write out, in the case we showed, the 0, 1, the 1, 1, and the P, all nice together, hopefully all in parallel. That's easy. However, when the data is small, and it's not going to constitute what we might call, what we would call a stripe, when you can't write all the data and the parity all at the same time, then you have to, it gets more complicated. So when you have to do that, you have to read the old data, read the old parity, calculate new parity, then write new data and write new parity. In other words, a single write, a single small write will turn into 4 IOs, 2 reads and 2 writes. So again, my client does one small write. My storage controller implementing RAID, Parity RAID, will do 2 reads and 2 writes. And we tend to call that the RAID penalty.
That's incredible stuff. And we have to do those 2 initial reads to calculate the new parity so that we don't have to do more reads.
Right. Right.
Now, let's take a look at that in perspective. If we have a host, and this is the right part of the screen, that sends 100 of these small random IOs, and 70% of those are reads and 30% of those are writes, how many back-end IOs will that workload generate? And we see here on the screen it's going to generate 190 IOs because of RAID penalty. And the formula for that is right there in front of you. The reads stay the same, but the writes get multiplied by 2 reads and 2 writes.
So we pay no penalty for the reads, but every one of those writes turns into 4, and so that's why our number goes up. That's
right. And this is very, very important for performance and block understanding, is front-end IOs are measured at the host are not the same as the back-end IOs that are measured at the RAID group or at the storage controller.
And we spent a fair bit of time of that in section 2, talking about the fact that it matters where you measure, whether you're measuring at the disks or you're measuring at the clients. So, RAID. We've tended to implement RAID at the storage controller, but it's not just RAID, right? The world is changing.
The world is changing. So if you look at the RAID, it doesn't cover one important bit, and that what we have seen in the last few years when you have multiple storage controllers within the same storage array, or we're using a technique called scale out. If we're using scale out and then we are not able to use just RAID to protect information, because if you lose an entire controller, everything behind that controller is gone.
So we want some method of effectively doing the same thing, of giving us a way of protecting our information, perhaps duplicating it in some way. And that bigger concept is erasure coding.
And what's interesting about erasure coding is that RAID is a partial implementation of erasure coding.
Right. So erasure coding is a bigger concept, and really what it means, it's the breaking apart of information along with creating a redundant set of information to go along with it that allows you to recover some of it. And so we can apply that up here at this storage controller level, in addition to having RAID, if you wanted to, behind this controller, to look something like this.
So in the erasure coding screen, we'll have a host that sends a bunch of IOs, and those IOs are redistributed along and among the storage controllers that we have that are scaling out, and creating the parity, which is also being redistributed.
So the picture looks a lot like RAID. There's a lot less assumptions of how you're creating that parity information, or the protection information, really.
And also some nomenclature is a little different. The erasure coding is usually addressed as an N plus M type of stuff. So in this picture, we have a 2 plus 1 again, 2 data bits, and 1 protection bit. And the protection bit could be parity, or it could be something else, it could be a mirror of the original bit. It depends on which particular erasure coding implementation is being used. And when we look at our symbols on top, the capacity is N, the protection is M, kind of makes sense, but the performance is different. And we want to leave it there as different because we're not going to go into explaining what happens with multiple controllers and how one controller could perhaps, out of the set of three, one controller could live in California where the other two are in New York.
Right. So it's not that we really don't want to talk about it. It's just you can't really give a pat answer to what the performance is going to be here because, as you pointed out, your controllers could be separated by massively different geographies. Vendors could be using different kinds of protection schemes. So the performance implications are very specific to your install, really.
And instead of saying it depends, we wanted to be indifferent. All right, and now let's pause and take a couple of questions. If David has anything worthy to discuss.
Yeah, I don't want to delay you guys too much because time's short, but there were a couple about RAID. First one was, why do you need to read old parity to calculate and write a new one? Isn't the parity only calculated based on the data being written?
Excellent question.
Yes. So, I've got a couple links at the end of the presentation that walk through it in very, very gory detail, which we had in here until we realized that it got overly complicated. The short answer to that is the parity information is calculated from every element in that the stripe, the stripe being all the drives that were participating. So if you were only writing enough data to go to one or two of those drives, then you could either pull all the old data off and make some modifications and calculate parity and write it all back down, or you can do what we showed, which is an optimization. An optimization is just to read the old parity and read the old data. But you're exactly correct. Parity is created from data, but you need either all of the data to create it, or the new data and the old data and the parity.
The way I look at it is the parity is there to protect you from losing some of that data, but the optimization here is using that same protection quality of parity to not have to read the rest of the data from disk drives.
Right.
So we only have to read what's changing, replace it with what's going to come, and then look at the old parity, and that's enough, mathematically, that's enough to create new parity. So instead of having multiple writes, you only have two writes after that.
Like I said, we'll have the links in the blog. If it doesn't make sense, feel free to ask Mark or I on Twitter, and we're happy to try to walk you through it.
Absolutely. Another question?
Yeah, why don't you move on? Thanks.
Okay.
All right.
We've discussed a lot now on single drives and how drives are grouped together, but let's see what really happens. I actually go back to performance numbers. Now when we kind of understand the implication of putting them together.
Yeah. We'll talk about implications here. I love this part. This is fun. So, hard drives. So, I have 4 hard drives here. Each one of them is a different color. We're back to these 4 kilobyte random writes. Like where we started, really. My numbers here are a little different. They're 106. I took some smaller numbers. It's okay, though.
As long as we know what the beginning blocks are, we can move forward.
So
these are 4 drives, and their performance put together, one on top of the other. Right?
So
because that makes sense.
So what happens before we change slides here, what's going to happen when I put them into a 3+1 RAID 5?
Are you asking me?
I'm asking you.
It'd be nice to ask to the group there. But I think what's going to happen is we're going to have RAID penalty.
Okay. And why are we going to have a RAID penalty?
We're going to have a RAID penalty because we have random writes in here, so they're all little. And every single write is going to be converted to 2 reads and 2 writes, because it's 3+1 you're asking me about. And reads are going to be serviced a little bit quicker than
they will.
Than the writes, depending on the information we saw earlier. So I predict a little less than 50%.
That's an excellent guess, since you helped me make the slide. But that's what we see. And if anybody cares a lot, I can even share the spreadsheet I use to calculate the math here. But we'd see, roughly from a straight RAID penalty perspective, that would drop us down to 169 IOs per second.
Well, that's actually a lot of loss.
That's a huge loss, which is why random writes are horrible for spinning media, right? We don't like random IO. So, is this all we would see in reality?
In reality, no. In reality, we're going to be paying some premium money to these big vendors, our employers actually, for the secret sauce, which is going to try to convert some of these random I/O into sequential I/O. And that secret sauce is going to add a little bit more back to the performance.
Right. So it's very unlikely that you'll ever recover everything, But hopefully by caching information intelligently, by trying to turn random IOs into sequential IOs in some way, you can recover a lot of that RAID penalty. And so maybe you're only taking a drive's worth of RAID penalty in the best case.
Which is kind of a poor managed approach if you're dealing with an enterprise level RAID implementation.
Okay. So like we did last time, let's compare this to Flash. So here are the same numbers I just showed on the previous chart. We're still doing 4 KB random writes. And those are the hard drive numbers. Here's what we would get with Flash. Once again, our hard drive just fades into non-existence.
Flash drives are a lot quicker.
They are. And so now we're looking at 5,045 IOs per second. And the fantastic thing about Flash is we'll pay no RAID penalty whatsoever.
I wish that was the case. It actually is irrelevant what type of drive you have. When you put them together into a RAID group, you will pay a RAID penalty regardless of the technology. And this is what you're going to see.
So our RAID penalty, if you paid really close attention, is less because the read performance on Flash is so astoundingly high. It helps kind of make up for this gap a little bit.
Well, percentage-wise, it's less.
Numbers-wise,
it is still in 5,000.
Actually, that's a great point, right? We're still losing almost 10,000 IOs per second, even if the percentage was less. And then once again, we've got this green over in the corner that is our awesome secret vendor sauce that helps you recover a lot of that.
Which is caching and the secret vendor. This is why the big vendors actually have a reason to exist.
All right. Now, you've done something crazy to us, Mark, to make my slide transitions here easier. What have you done?
Well, what I've done here is I said that IAPS is a very interesting metric, but let's take a look and see exactly the same numbers we have in megabytes per second. Kind of flip them a little bit to the side. And to get those megabytes per second for everybody who's been attending, you should remember you multiply the IAPS by the size of the IOs. So there are 4 KB and those thousands of numbers that we had before. If you put them all together in megabytes, the hard drive is going to be able to do 1 megabyte a second. If we put them all together and assume they're all stacked up, it will be 79. And then if we use caching rate controller, it will be 59.
Okay.
So the question I have for you, Ken, is 59 megabytes per second seems kind of small. Any way we can make it bigger with exactly the same drive?
I thought you were going to change the question on me. Yes, we can. And we're going to do it 2 ways. We're going to cheat. One, I hate talking about megabytes per second or megabytes per second with small random I/O because we just normally don't do that. We normally do talk about megabytes or megabytes when we talk about large I/Os. So first thing I'm going to do is I'm going to switch to really big I/Os because that way I'm doing more data.
By big, you mean like 8 kilobytes?
Yeah, like 128.
128 kilobytes.
Right. So we're going to, we could go much bigger, but my data is from 128, so that's what we're going to use. So what that does is it gives us a lot more data, a lot less packet header information that it describes each bit of data. So we're going to do that. And number 2, I'm going to cheat by not doing a RAID penalty anymore. So I'm going to switch. I'm going to switch from 100% writes, all writes, to all reads, so I don't pay a read penalty anymore.
And also make them sequential.
Right, and that's true. And then we're going to go to sequential.
So when we switch the I/O size from 4 kilobytes to 128, the random to sequential and writes to reads, look at the megabytes per second, the 3+1 RAID group on the flash devices is going to be 5,685 megabytes per second.
Yeah, technically I was kind of I was sneaking on the back end. We switched from megabytes because your math was megabytes to the SNIA numbers, which are all megabytes, but it doesn't matter. These numbers are so high. We're looking at nearly, 5.6 gigabytes of data.
I love that number. Can I get that number on my computer, on my PC, on my flash, on my laptop here?
Right, because this raises the question of if these drives are so fast, why would you ever buy more than 3 of them, number 1? And the answer to that would be capacity. But
clearly you shouldn't.
Clearly you shouldn't. and why aren't we all just rocking with these huge data rates? So let's just assume you had an all-read workload. Is this the data rate you would see?
Yeah, that's what Netflix sees, right?
So let's move to the next one here and walk out why, right? So,
whoa!
if you wanted to get 5,685 megabytes per second, you would need 10 6 gigabit per second SAS connections. You would need 6 PCIe 3.0 lanes. And then that's on the back end of that storage controller, another one on the front end of the storage controller. You'd need 4 16 gigabit fiber channel connections. And I don't know, Mark, you tell me how many hosts we'd need.
Wait a second. This is astonishing. So what we're trying to tell me here is if I were to use the potential of these 4 drives in a normal storage array, my bottleneck is going to be my storage controller.
Probably. I mean, it
or the back end, actually,
right.
all 3 of those in the middle are going to be the bottleneck.
Right.
I just can't even get to the potential performance of these 4 drives.
Right. You know, and lots of times it's just core infrastructure issues, right? We just don't have enough pipes to push that much data, even if your storage controller could do it.
Even if I'm assuming my clients are going to be able to do this.
Right.
This is really big. So what we try to say is if we use the part number 2 idea of moving the bottleneck away, what we're trying to do here is to say, let's get rid of this entire middle stuff.
Well, I'll be a little softer in that and say that this is certainly something that we're seeing in the industry, is people realizing the drives are so fast, how do I get a better access to them? And so you see there are various movements in the industry to take those drives and put them into the client. Now it doesn't solve all the problems because there's a reason we did them where we did, right? How do you protect them? How do you share that data? How do you do data locking if they're just in the clients? You know, you're going to have to go off and create a cluster of clients. What do you do? But there's certainly a trend.
And there's certainly new tech that's either about to give that or already claims that.
Right.
And being vendor neutral, which is going to stop at that.
But it's going to create a whole interesting industry here of how do we deal with that much performance when your clients can actually access it and use it.
That is incredible. So 4 drives are so fast that the rest of your infrastructure is now kind of lagging behind.
Potentially. We were doing 100% reads, but potentially, absolutely. And, you know, just imagine what would happen even if they weren't 100% reads, if you had 100 of them because you needed them for the capacity. Right? How do you possibly use the performance of 100 SSDs or flash?
So then I can summarize and say that this picture where we take 4 drives and their abilities to execute and deliver some performance, this is why block is the foundation of storage performance. We need to understand how those drives in the back and all the way in the back are performing to understand where the bottlenecks are and how those bottlenecks are distributed throughout the entire solution under test between those drives and the clients.
Absolutely. And I'll even go a little bit farther and say it's not just in this context of flash, right? Understanding the hundreds of thousands of hard drives out there and how and why we protect them the way we do. This is a core and critical component both to understanding my performance today and where my performance is going to go in the future, whether you chose to continue to use hard drives or you make the move to flash.
Incredible. And as we said in the very beginning, since all the data ends up in the block storage, it's important to know how that works.
Absolutely. And that is the end of the planned content. David, what kind of questions do you have in our 3 minutes?
Boy, did you just nail this, the timing. I'm impressed. One was really for me, so let me just hit it because it keeps coming up. People want to know where they can get this presentation. It's on the SNIA Ethernet Storage Forum website. It's under Knowledge Center, Webcast on Demand. And in fact, the PowerPoint and PDF versions of this presentation are already up there posted. The link to this Bright Talk webcast will be up shortly as soon as we get that link from Bright Talk. You know, we've only got time for one real quick one, so let me just ask this one. Does it help SSD write performance to cache the data before you write it?
I will say yes, because memory is still faster than flash. And so the more you cache, hopefully the less you will ever have to write.
And then you can write them in more condensed matter within the same block.
That could be tricky.
And therefore cause less data movement, trying to save it.
The rest of the questions, I guess, we're going to have to take offline, but we got a bunch, and thank you all, and please rate this presentation. We appreciate
and actually, let me throw a comment on the rating in there. If we say it before it dies. This is not Mark or my day job. We're loving doing this. We love the feedback that we've gotten on it. But if you enjoy these and you find them useful, please rate it and let us know, because that's how we let our managers know that our time is being spent in a in a way that helps you.
And do follow us on Twitter. The Twitter handles are right there, and all the links are also there. And depending on how this session is rated and how it goes, we will plan the next one at some point in 2016.
Probably on file performance.
Probably on file
further. Please join us.
Thank you very much, everybody. It was a pleasure being here with you today.
Heck of a lot of fun. Thank you all.
Thank you.